3.2, solving quadratic equations by factoring. Up to this point, you have or should have completed the grade 10 review of factoring and lesson 3.1, which involved factoring polynomial expressions, specifically quadratic expressions, that also happen to involve more complex pieces in place of the variable itself. So now we're going to introduce the idea of an equation. And an equation is not the same as an expression because it has this equal sign and something on the other side. So we still have ax squared plus bx plus c, but now we've got y equals. So we're able to graph this because we've got two variables. We've got an x coordinate and a y coordinate. The key thing is that a, b, and c have to be real numbers, which you don't know about imaginary numbers, so that's not going to be hard, but a has to not equal 0. Now the reason that that needs to happen is because anytime you multiply by 0, the whole piece that you're multiplying becomes 0, and so all of a sudden this term that we have as ax squared becomes 0, it becomes completely negligible, and so we're left with y equals bx plus c. This should look very similar if we replace this and this. All of a sudden we've got slope-intercept form and we're dealing with an entirely different beast. The graph of y equals mx plus b is very, very different from that of a quadratic. And we should have seen that in our activity that we did actually at the beginning of this unit. So some examples are y equals 2x squared plus 3, y equals negative x squared plus 7, and I apologize for how this shifted when it printed, y equals x squared. These are all quadratic equations, and they cannot always be solved by isolating the variable. We can't just get x by itself. This one, absolutely, we could. We could just take the square root of both sides. Even this one here, we could subtract 7, switch the sign, so x squared is positive, and take the square root. And even our first one. So all of these examples are entirely factorable by isolating the variable. But that is not always the case. All of these ones only have x squared. They don't also have that bx term, that term where x has an exponent of 1. So what we're going to do instead is we're going to use factoring to actually solve this. And it strictly depends on this property here, the zero product property. That means that anything when they're multiplying to equal 0 implies that one of the two pieces needs to be 0, or they both are the same value, and that value is 0. So any two things multiplying to equal 0 implies one of those two pieces also equals 0. Bearing that in mind, let's give some of these a shot. So step 1 is having everything equal to 0 so that we can apply the zero product property. See, we are equal to 0. From there, we want to factor. We want to find out what were the pieces that multiplied to give me this polynomial. So this is a simple trinomial. So I am going to find the product, the factors that give me the product of 9, and that add together to give me positive 6. Well, factors of 9, 1 and 9, or 3 and 3. 3 and 3 plus 3 gives me 6, so I can factor this out as x plus 3 squared equals 0. So in this case, we're using the statement a equals b equals 0. We've got two of the exact same thing, and they're set equal to 0, so they both have to be equal to 0. So we can kind of solve this from there. We've got x plus 3 equals 0, because that is what both of my factors are of this trinomial. And I'm going to solve for x. Now from here, it's strictly isolate the variable. So I subtract 3 from both sides, and we've got x equals negative 3. And x equals negative 3. I will always have two answers. It's just a matter of them being the same in this case because my two factors, right, remember it's squared, they are both the same. So that's how we apply the zero property. Let's try it out with this one. It's still a simple trinomial, so we can still use our product and sum method. So I like to think on the side of my page when I think about products and sums. In this case, I can spot it pretty quickly. 21 has a factor of 3 and 7. I'm going to have one of them be negative, but they need to add to a positive value, so my smaller value is going to be the negative 1. So when I factor this, I've got x minus 3 and x plus 7, all equals 0. This uses the property that either a equals 0 or b equals 0. So we're going to do both. We've got x minus 3 could be 0, in which case x would be positive 3. Alternately, x plus 7 could be equal to 0, in which case x would be negative 7. So now I have two possible answers. Now if you plug them both in, they both actually work. So they are both legitimate answers, and we can keep them both. You now have two answers for these quadratic equations. Let's try another one. Now this one is a complex trinomial. I look to see, can I factor out this 2 and isolate my x squared and make it a simple trinomial? The answer is no. 2 does not go in evenly to 9 and 5, so I'm going to have to complex factor this. Now, if you can spot quickly the fact that 2 times 5 is 10, factors of 10 are going to be 1 and 10 for this one in order to be able to equal negative 9. Or you can guess and check, whichever one kind of floats your boat. I'm going to do the crisscross since I already think I know the answer. So I need it to equal 2x squared on this side, so I'm going to go 2x and x. On this side I need it to equal negative 5, so it's going to be negative 5 and 1. The reason I do that is to get my 10. I'm going to have the 2x multiplying by the negative 5. Negative 5 because it needs to multiply to give me a negative value, and my larger value when I add them is going to be negative to produce a final negative sum. Multiplying across, I've got x going diagonally this way. I've got negative 10x going diagonally that way, which gives me a total of negative 9x. So it works, and these are my two sets of brackets. So 2x plus 1 and x minus 5. Again, from here, we're going to be using that property of a equals 0 or b equals 0. You don't need to be writing this property down, but if it helps, definitely do it. So option 1 is 2x plus 1 equals 0. Doing this, we've got to isolate the variable, and we kind of peel away the layers. So we've got 2x equals negative 1, divide by 2 on both sides, x equals negative 1/2. You are allowed to have fractions as answers. The reason that this is allowed is because it is still a real number. The only things that aren't real numbers are non-repeating decimals. So things like the square root of 2. Well, technically that's even a real number. It's just irrational. So we've got infinitely many possibilities of answers as long as we don't get into imaginary numbers. But again, we haven't learned about those. You won't in high school. And so you don't need to worry about them. You will always have two possible answers until we realize that there's some problems that we run into, but that'll be later in the unit. Whenever you're factoring, you should have two answers. So our other option is x minus 5 equals 0. That one's a little nicer to move around. X equals positive 5, and that's my other solution. So again, two answers. Totally fine. Plug them into your original equation to check that they work, just to be sure of your answer. 5 squared is 25 times 2 is 50. Minus 9 times 5 is 45 minus 5, and that does equal 0. Alternately, negative a half squared is a fourth, times 2 is a half. Negative 9 times negative a half, we're going to be adding 9 halves. So that's 10 halves in total. Subtracting 5, well, 10 halves simplifies to 5. So 5 minus 5 is 0, and that one works as well. Again, I did that by mental math. You are more than welcome to write it out. I've been doing this a little bit longer than you have, so I'm going to be a little faster. This one looks great. It's already factored, right? Problem. Not equal to 0. So we're going to have to expand our current binomials that are multiplying, move the 3 onto the other side, and set our equation equal to 0 before we even think about factoring and coming up with an answer. So this is one that is frequently, people just set them equal to 0 and go from there, but they totally forget that it's not actually 0, it's 3. And we can't assume 1 is equal to 3 and 1 is equal to 1 because those are factors of 3 because we don't know which one's which. So we gotta go from there, and it could potentially be like fractions. We have no idea. So set it equal to 0, first step. So we need to FOIL this out. So remember, firsts, outsides, insides, lasts. And we get 2x squared plus 2x minus 3x minus 3 equals 3. Now we're going to simplify and move this 3 over all at once, collect like terms, subtract 3 from both sides to get this equal to 0. So we're got 2x squared minus x minus 6 equals 0. Now I can factor. I look for a greatest common factor just in case there isn't one, since 1 is my coefficient in my middle term. So I'm going to look to factor it otherwise. 2 times 6 is 12. Which means that I'm looking for factors that will, of 12, that'll get me to -1. So that's going to be -4 and -3. I'm going to factor this out using my other complex trinomial method. So that's 2x squared minus 4x plus 3x minus 6 equals 0. Take your common factors out of both of those. We've got 2x times x minus 2 plus 3x minus 2. Again, I know I've done this right because my factors inside those brackets are the same. I can factor that out since it's common to both terms, x minus 2, and I'm left with 2x plus 3. Am I done? No, because I haven't actually solved for x yet. And that's what I've been trying to do this whole time, is solve for x. So I'm going to use that a equals 0 or b equals 0 property. I'm going to take x minus 2 equals 0. So x would be positive 2. Or I've got x, or 2x plus 3 equals 0. Move the 3, gives me 2x equals -3. So x equals -3 halves. And those are my two answers. Again, I can plug and chug to check. Last example like this, we've got 2x squared equals 4x. Again, red flag. I want this thing equal to 0 all the time if I'm going to try and factor. So we've got 2x squared minus 4x equals 0 instead. Always check for greatest common factors first. In this case, I do have common factors. I'm going to take out 2x from both terms, and that leaves me with x minus 4. Nope, not x minus 4, x minus 2 equals 0. So we do still have two pieces here. They just look a little bit different than in the previous examples where we had two binomial factors. Here we have a monomial of 2x and a binomial here. The same rules still apply. We are still going to use that either a equals 0 or b equals 0 principle. But this time we've got a monomial of 2x that we set equal to 0. If we divide this by 2, 0 divided by anything, you can't divide nothing into any number of groups, so it's still going to be nothing. Alternately, we've got x minus 2 equals 0, in which case x would equal positive 2. Therefore, I still have two answers. So our remainder theorem is actually quite helpful because it will help us check to see if something is a factor of a polynomial. Okay, so this 15, again, should be over here. Sorry about that. So remainder theorem is that for any polynomial, if we try and figure out if that's the binomial, then its remainder can be figured out by plugging in that constant term back into the polynomial. So this sounds pretty weird. So our remainder, if it is actually a factor, should be 0. It should divide into it beautifully to give us a product of 0, which is going back to this definition up here, where the factors, when we plug them in, will produce a 0 value. So let's just make note of that. So no remainder means it divides evenly, and therefore it should produce a 0 value. So using this one, we've got x plus 3. Well, we're in the theorem, we're told x minus a. So we're actually going to be saying that a is negative 3. We need to switch that sign because we've got that negative out in front, and we need a negative and a negative to give us that positive value. From here, plug and chug. 4 times negative 3 squared plus 12 times negative 3 plus 9. That's 4 times 9 minus 36 plus 9. 4 times 9 is 36, so these pieces are going to cancel, which leaves us with 9. Therefore, this is not a factor. Looking at B, another typo there. Maybe that would make room for the 15. Again, we're dealing with x plus 3, so a is going to be equal to negative 3. And we plug and chug. 2 times negative 3 squared plus negative 3 minus 15. Well, that's 2 times 9 minus 3 minus 15. So that's 18 minus 18 equals 0. Therefore, x plus 3 is a factor of 2x squared plus x minus 15. The reason this works and the reason we have to change our sign when we plug it in is going back to our previous question. We can look at our binomial is x minus 2. So notice that x equals 2 is our actual value of x. The same thing happens here. If we set x plus 3 equal to 0, we'd have to move that x around, and so we would get a equals minus 3. So that's where that's coming from. So you can figure out if something is a factor without actually having to try and divide it out. Because you don't know how to divide binomials into polynomials, you learn that in grade 12. So R5 is our solving problems using quadratic equations, but I like to integrate it into all of these lessons so that you can kind of see how all of these different methods that we're going to be learning about in terms of solving equations actually applies to the questions that we're eventually going to get to, because not every question gets tackled the same way. So our first question is dock jumping is a dog event in which dogs compete for the longest jumping distance from a dock into a body of water. So you can think about yourself on a dock at the lake, and you run off and jump into the water while dogs do the same thing. So they run, they jump as far as they can, and the person that lands the farthest is the winner. It's a pretty cool thing to actually see. So in this particular case, the path of a Jack Russell Terrier, which is a type of dog, on a particular jump can be approximated by the quadratic function h of d, so the height compared to the distance is equal to -3/10 d squared plus 11/10 d plus 2, where h is the height above the surface of the water and d is the horizontal distance the dog travels from the base of the dock, both feet in. Determine the horizontal distance of the jump. So h is this, and d is this, just from the end of the dock here to where he hits the water. So that horizontal distance is like my x value, and so I'm going to have to solve for x, right? Because it's my input here. So what I'm going to do is, what is the height when he hits the water? Well, it would be 0. So we're going to plug in the height equals 0, and we're going to solve for d. So we need to solve for d. We're going to plug in 0 equals, and then the rest of our equation, because we don't know our d value. So our F word in math is showing up again. That's fractions. We want to get rid of them. And so in this case, because we actually do have a 0 on the other side, we don't need to worry about factoring a 10th. Instead, we can just multiply both sides by 10, and we're going to be able to cancel out that denominator. So everything is going to be multiplied by 10 on the right-hand side, and 0 is going to multiply by 10 on the left. So you can think of it as multiplying it this way. You could also think of it as multiplying each term by 10. Either way, we're doing the distributive property. Anything multiplied by 0 is 0. So my left-hand side stays the same. But now I've got 10 divided by 10, 10 divided by 10. So the only one I'm actually going to be multiplying by and getting a different value for is my third term. So I've got -3d squared plus 11d, oops, left that out of that one, and plus 20. From here, I've got a complex trinomial I've got to deal with. 3 doesn't factor out of 11 and 20 very well, but it does have a negative out in front of it, and I hate negatives in front of that first term. So I could factor it out and just leave it out in front and hanging out there. But again, because I have this equation with 0 on the other side, 0 is the most powerful tool for multiplying and dividing. So what I'm going to do is I'm going to multiply everything by -1. And what that does is multiplying like by like is positive, and then opposite signs gives us negative. So it's going to switch the signs on all of my terms. I'm going to multiply by -1 on the other side as well. But again, 0, that powerful tool that turns everything into itself. So the left-hand side stays the same, but now I've got 3d squared minus 11d minus 20. Now I've got an equation that I want to be able to factor. This is a little bit monstrous because when I start doing my complex trinomial factoring, I'm dealing with -60 as my term that I need to find factor pairs for. So It might take me a while to get there. 6 and 10, that's not going to work. 3 and 20, I'm going the wrong way. But I can figure out that actually 4 goes into 60 evenly multiplied by 15. Now I need opposite signs producing a negative when we add them, so I'm going to do negative 15 and positive 4. From here, complex trinomial factoring, you could do the crisscross method. I'm going to do the sort of split binomial method. So I've got 3d squared minus 15d, and again, it doesn't matter which one you put first. And then plus 4d minus 20. So again, I've just split that 11d into 2 pieces. Keep going. Imagine that this is divided. Factor something out of the first 2 terms. I can take out 3d, leaving me with d minus 5. Out of the second one, I can take out that 4, so it leaves me with d minus 5. Again, I know I'm doing this right because I ended up with the same binomial in the brackets. So I've got d minus 5, and when I factor that out, I'm left with 3d plus 4. Still not done. I still don't know my horizontal distance, my d. So I'm going to plug these in. D minus 5 equals 0, so d would be positive 5 meters. Or I could have 3d plus 4 equals 0, so d equals negative 4/3 meters. We look at what is happening in this scenario. Would a dog jump negative 4/3 of a meter? No, which means we only actually have one legitimate answer, and that would be d is 5 meters. Now you can check this by plugging it back into our original equation, and it will work. I promise you, because I did it myself. So again, when we're thinking about word problems, and in general, when we're solving these equations, when we're solving math problems, we want to think, does that answer make sense? Negative meters in jumping definitely would not get the dog any sort of prizes. That's not what he's trying to do. He's trying to go forward, not back. So we don't want that negative value. This one's a little bit different. Again, you'll notice I like to draw pictures for word problems because they just help me think a little bit and give me some context. So the length of an outdoor lacrosse field. Now lacrosse, FYI, is a rectangular field just like soccer, just like football. And we're told that the length of it, so length, is 10 meters less than twice the width. So we need to double the width, and then we're going to take 10 away. It's 10 less than that. And then my width is just my width. So you'll notice that I'm using variables that apply to this scenario, h and d in the previous question, L and W here. I personally like to use variables that match my scenario because it helps me keep on track in terms of what I'm solving for. You could use X and Y, that's completely up to you. So that deals with my first sentence. The second sentence, the area of the field is 6,600 meters squared. Well, what can I do with area that relates to length and width? Well, I can write the formula for it. Area is length times width. So to work backwards and figure out my dimensions of my field, I'm going to have to apply that area equation, but then plug in my different variable values here. So I've got area equals length times width, but we've got 6,600 as my area equals length, which I'm now going to write as 2w minus 10 times the width. Now the reason I do that is we can only solve for one variable at a time if we only have one equation. So I can't have L and W in there and be able to figure out what they both are because there's infinitely many possibilities. It could have been 66 by 100, but that wouldn't fulfill our requirement. So I'm going to use the parameters given to me in the question, that twice the width minus 10, to have just one variable in my equation. Now I can solve for W. But I can't just go, okay, this is equal to 0 and this is equal to 0 because my equation right now is not equal to 0. So my 0 property won't work. I need to expand, move it around, set this whole equation equal to 0. Then I can use those 0 properties. So for now, I'm going to leave that on this side while I expand. We distribute to get 2w squared minus 10w. Now I can have it equal to 0 where it's 2w squared minus 10w. Remember, we do opposite operations. Right now we're adding, we need to move that, so we need to subtract. The reason we're subtracting instead of dividing is I need this equal to 0. I need this gone entirely. If I divide 6,600 by itself, it goes into itself once. That leaves me with a number still. So I'm not going to divide, I just strictly need to move the whole thing, all those pieces to the other side, which is why I subtract. From here, I'm factoring. I look for a common factor first. Luckily, there is one. And that leaves me with 33,000. Okay, now that looks like a huge number. So what I do to help me think this through, to figure out all my factors, is I prime factorize. So I'm just going to do that off to the side. So you could start working with factor pairs. That's another option. But I'm going to do it this way. So these are all my prime factors. So I'm looking for a way of combining them that's going to let me have two values very close together. Well, if I actually take 11 times 5, that gives me 55. If I take the other 4 factors, 2 times 2 is 4, times 3 is 12, times 5 is 60. I have a difference of 5. So I just need to decide which one I want to be negative. It's going to be the 60 because I end up with a negative middle term, a negative b value. So I'm left with 2. And then because it's a simple trinomial, that's all I needed to do. I just needed to find my factor pairs. And now I've got w plus 55 and w minus 60. Again, we are not done. That 2, you could divide it out, but really it's not attached to a variable. 2 is 2. It's not ever going to be equal to 0. We can't say this. Not possible. So one of these two pieces needs to be 0. Again, we're working in meters, so add our units there because it is a word problem. Which one makes sense, or do they both make sense? The answer is negative 55 meters does not make sense as a width. Why would we talk about negative meters as a width? So our only answer is the width is 60 meters. But we're asked for the dimensions. So that means I need both the length and the width. So I'm going to go back to my original equation of 2w minus 10 equals 2 times 60 minus 10, which would be 120 minus 10, so 110 meters is, oops. My length. There you have it. So you've got lots of practice questions to do for 3.2. You can look in your workbooks. I definitely recommend starting there. And then if you want to continue on, you can always find more examples online.